All right, what we're studying right now are improper integrals. So this will be a hopefully short lesson on improper integrals that I've actually accidentally let you run into a couple of times. An improper integral seems impossible because it'll be unbounded. Like it might say that you want to take the integral of 1 over x dx as x goes from 0, well 0 is undefined, as x goes from 1 to infinity. And so you have 1 over x, by the way, looks like this. And you're going from 1 out to infinity. And so you think, well, that's going off to infinity. How could I ever add that up with an integral summation tool? It's a lot like geometric series, how you can add up numbers if they're getting smaller and smaller. That's an indication that you probably can find the sum. Like for instance, it's like if you had a runny faucet and the water kept dripping out of the faucet, and then you tighten the faucet, and every few weeks you might notice a drip that comes out, but you're not worried about that. As opposed to you tighten the faucet and you still hear this constant drip, drip, drip. You virtually tried to close it, but there's still so much water running out that could affect your water bill, as opposed to you've squeezed it shut. So there's lots of things in life that we can talk about that have been squeezed shut. We may get a little leak or something, but virtually nothing else is getting through and it converges, as opposed to things that aren't squeezed shut and air, water, numbers, whatever it is still leaking out. And it's hard to tell without mathematics which ones have which ones have an infinite sum and which ones don't. So what we're going to do is sort of like use substitution. We're going to pretend like that it's not a problem. I'm going to take the limit, we use b a lot, as b approaches infinity, and I'm just going to look at the limit of 1 over x dx. I'm looking at the integral of 1 over b of 1 over x dx. So I'm just going to take this integral and then see if the limit exists as I go out to infinity. All right, so b approaches infinity. All right, the integral of this is ln x as we go from 1 to b. So I'm holding off on the limit for a minute, and I get ln b minus ln 1. I don't need absolute value right now because I know they're both positive, but you could put it on there. Now when you fill in infinity, I get ln of infinity minus ln 1, which is 0. Ln of infinity is infinity, so this one means that this sum does not exist. And so you could say that this diverges. By the way, the graph of ln x looks like this, just to refresh your memory. It has a vertical asymptote. It does not have a horizontal asymptote. As it goes out to infinity, it goes up to infinity ever slower, but it's still getting higher and higher. And so the limit of infinity is just infinity, which, by the way, backs up what happens if you have infinity over infinity. If you have infinity over ln infinity, you have infinity over infinity, but it wouldn't be a 1-to-1 ratio back when we were talking about L'Hopital's rule. So let's do another one. So another example is the integral from 3 to infinity of 1 over x squared dx. Now this one is going to exist. I know that because I've done it before. Another thing you'll learn is if you have a power greater than 1, it's going to come a whole lot closer to the axis a whole lot sooner. And for all practical purposes, whatever's added back here is virtually so tiny that it doesn't affect your sum. That it's what I would call squeezed shut. The correct word would be it converges. That last one diverges. So I'm take the limit as b approaches infinity of the integral from 3 to b of x to the negative 2 dx. So I have the limit as b approaches infinity. The antiderivative of this is negative 1 over x from 3 to b. So that gives me the limit as b approaches infinity, negative 1 over b minus negative 1 over 3. And so when you fill in infinity now, this gets infinitely small. 1 over infinity goes to 0. And I get a number, minus negative 1/3. And so this converges to 1/3. And by the way, this is leading up to talking about series that will converge, but right now we're just talking about improper integrals. Now I'm going to do a couple more examples, and then you'll have some to work. What if I have the integral from 0 to infinity of e to the negative x dx? All right, e to the negative x looks like this, exponential decay, from 0 to infinity. We're wondering if it squeezes shut. So I'm going to take the limit as b approaches infinity, 0 to b of e to the negative x dx. Technically, I should use u substitution here. I shouldn't integrate anything but e to the x or e to the u. But if I let u be negative x, I see I'm going to have to compensate for this negative as I'm going backwards. So the integral of an exponential function is you copy it down. You say over ln of the base, but that would just be over ln e, which is 1. And then you undo your chain rule. So I have this extra negative in here from 0 to b. So I have the limit as b approaches infinity. This gives me negative 1 over e to the x from 0 to b. So that gives me the limit as b approaches infinity of negative 1 over e to the b minus negative 1 over e to the 0. Remember, I've said so many times, don't neglect filling in 0. When you put an infinity right here, 1 over infinity is going to go towards 0 when you're taking a limit. And I have minus and negative. E to the 0 is 1, so I get an answer of minus negative 1. And so this actually has a sum of 1. Let's see, let's do this one. The integral from 1 to infinity of 1 over x squared plus 1 dx. These are all examples in your book. I'm going to take the limit as b approaches infinity. And usually we use b. Like I said, we don't have to. Okay, that's an arctan. And so, by the way, 1 over x squared plus 1 looks something like this. It doesn't, it's never undefined on the bottom. Has a horizontal asymptote of 0. And we're wondering if it converges or squeezes shut. So I have the limit as b approaches infinity. This is an arctan, so I have 1 over a, which is just 1. Arctan of u, which is 1 over a. Arctan of u over a, which is x over 1, from 1 to b. So I have the limit as b approaches infinity of arctan of b minus arctan of 1. All right, now arctan of infinity. Let's see what that is. Remember, inverse tan can only look in quadrants 1 and 4. And the graph of tan from quadrants 1 and 4 look like this. So when you're doing arctan, you answer when tangent's going to, the tangent of what is going to infinity. And this happens, tangent goes off to infinity at pi over 2. And the arctangent of 1, the first thing you encounter is pi over 4. So you get 2 pi over 4 minus pi over 4. And so our answer is pi over 4. But just a minute, I'm looking in the book, and the answer is pi over 2. Oh, I was going 1 to infinity. The book, I'll change it to the book in case you're looking in the book. This is fine the way it is. But if I'm going from 0 to infinity, we'll get the answer that the book had. Interesting to look at it either way, doing your arctan. All right, so if this is arctan of 0, Okay, arctan of 0 is 0. And so you just get pi over 2, because the one in the book was that I was trying to copy was going from 0 to infinity. All right, now sometimes you might have to do 2 of them, where you have, I'm trying to look for one in the book, let's see, where it looks innocent at first, like this, and the book is example 6. All right, on example 6, you have the integral from 0 to 1 of 1 over the cube root of x. And it looks innocent because it doesn't look like that it's unclosed. It's going from 0 to 1. But if you look at 1 over the cube root of x, that graph's really weird looking. I probably should go to Desmos and graph it. But if you fill in 0, it's undefined. And so, and then if you fill in 1, you get 1. And let's go on and talk about it. If you fill in 8, you get 1/2. So way out here, you get 1 over the cube root of 8, or 1/2. So it's going like this, and it's got a vertical asymptote right here at x equals 0, so it's an improper integral. I want to know, like now, is it squeezed shut this way? Because you're only going to 1. So you're looking to see how close is this going to come to the axis by the time I get to 1, 1? Is it going to be something I can add up, or something that's going off to infinity? So you got to know which one of these two numbers goes off to infinity, which would be this one. So I'm going to take the limit as b approaches 0. The integral from b to 1 of x to the negative 1/3 dx. Then I'm going to take the integral as b approaches 0. Add 1, you get x to the 2/3 over 2/3, or times 3/2 from b to 1. So then you have the limit as b approaches 0 of 3/2 if you put in 1, and if you put in b, you get, leave some room to write. If you put in b, you get 3b to the 3/2 over 2. Now if you work your limit and fill in 0, you get 0 on the top. So you just get 3/2 for your answer. And so it does converge. Apparently this gets really, really close to that line, and it squeezes shut. Here's another one that's interesting. Example 7, or example 8. Either one of those would probably be good to do. I'll do example 8. I'm going from negative 1 to 2 of 1 over x cubed dx. Now be careful. You could just jump right in and integrate this from negative 1 to 2, and you've never had to worry about this. But you would get the wrong answer, because do you see this is undefined at 0? So now we've got to look at the continuity of it and look at the domain. Like for instance, what I was saying is you could take the antiderivative of this from negative 1 to 2 and never even really realize that there was a problem in the middle where 1 over x cubed, I don't know exactly what it looks like, something like this, and you're going from negative 1, just going off to infinity, and then continuing to 2. And what you want to know are these things squeezed shut enough, close enough to 0 to where you can get the sum. So look at where it's undefined at 0. So I'm going to integrate this from negative 1 to 0 of x to the negative 3 dx. Then I'm going to integrate it from 0 to 2 of x to the negative 3 dx. Usually there are a little more blatant problems than this, but from now on, we've got to watch out for stuff like this. If it says to go from negative 2 to 2 of 1 over x dx, don't find yourself just doing ln, because this thing's undefined at 0. I'd have to break it up into 2 parts. It's an improper integral during that time. All right, so now the problem area here is 0. So I'm going to take the limit as b approaches 0 of the integral from negative 1 to b of x to the negative 3 dx plus the integral from b to 2 of x to the negative 3 dx. When you add 1, you get x to the negative 2 over negative 2 from negative 1 to b, and x to the negative 2 over negative 2 from b to 2. Let's get some room to work over here. All right, so moving up here, I'm still carrying this limit as b approaches 0, where it's undefined. I'm going to rewrite this as negative 1 over 2. I'm going to go ahead and fill in the b squared minus negative 1 over, now I'm going to fill in negative 1. So I'm rewriting this, I'm sorry, let me be clear. I'm making this negative 1 over 2x squared. And I'm filling in b right here, and now I'm filling in 1. So I get negative 1/2. And that's the first part. And then the second part is right here. I'm going to have plus, and this is all in terms of the inside the limit. I'm going to have negative 1 over 2, and I'm putting in 2 to the x squared 4 minus negative 1 over 2 b squared. And then when you fill in b is 0, then you get 1 over 0, you get 1 over 0 here, and so you got a sum that's undefined, because you can't add this, which is technically going off to infinity. If the bottom's getting smaller, the fraction's getting bigger, and so this one diverges and does not have a sum. If you look at a graph of it, I believe you can almost sort of see it. I think it's pretty far away from the axis during that time from negative 1 to 2. It's got a lot of open area, but you can't really tell that actually until you take the limit. So a lot of them aren't that tricky. And you'll have some probably assignment out of the book and the worksheet.